Welcome, everybody, to a NASA's Universe of Learning science briefing for the Museum and Informal Education Alliance and Solar System ambassadors. Welcome to you who are here live and those of you listening in the future. And just a reminder, thanks for coming to these and letting us know what you want to hear about. This was a bonus event because of interest that this community said they wanted to know more about. So thank you for sharing that. So with that, we're going to turn it over to Dr. Lipo.
Hello, everyone. My name is Dr. Kelly Lipo. I'm at the Space Telescope Science Institute, and I'm really glad that you all were able to join us for today's special NASA's Universe of Learning science briefing. When I was in grad school, became somewhat obsessed with novas. I took this class on astronomical transients, which are things that go flash in the night. And I got assigned to do a report on novas. And they just, there seemed to be so much that we don't understand about them. So I thought that they were really cool. And I included perhaps a too long section on novas in the introduction to my thesis. So when the Museum and Informal Education Alliance came to us and said, oh, there's interest in this upcoming nova, I was like, oh yes, perfect. Let's do it. Let's do a special science briefing. Today we have two speakers to tell you all about the predicted T Coronae Borealis nova. We have Elias Aydi, who is a NASA Hubble Fellow from Michigan State University. And we also have Chick Woodward from the Minnesota Institute for Physics at the University of Minnesota. So how we're going to do it today, we are going to have our two speakers. Elias will tell us about exploring nova interruptions, and then Chick will tell us about the recurrent nova T Coronae Borealis. And then after that, we're going to go through some resources that we have from NASA's Universe of Learning about novas and also star formation in general that you can use with your own audiences. And so with that, I will turn it over to Elias, our first speaker.
Thank you so much, Kelly, and thank you for having me today here. So today I'm going to be speaking about exploring nova eruptions, and I'm going to tell you about the latest advancements in our research into novae. So before I start, I want to give a quick intro about the type or the evolutionary stage of some stars like our sun in particular, and how they change throughout their life. So this is what we think the life cycle of a star like our sun would look like. Initially, the star is born from a large molecular cloud of gas and dust, and then the star will start burning hydrogen into helium, which the sun is doing now, sending us all the energy due to this nuclear reactions in this core. But at some point, the hydrogen, which is the fuel of the star, will start running out in the core, and the star will start dying. When this happens, the star will swell up in size. It becomes something we call a red giant. So our sun will be so large, its outer layers will engulf all the inner planets like Mercury, Venus, and Earth. And this is the phase of evolution where we call, as I said, a red giant. And during this phase, the star will lose a lot of materials via what we call stellar winds. Later on, after the star lost all of its outer layers, the remnant core of the sun, which is now a hot body that is cooling slowly without any nuclear reaction in its center, we call it a white dwarf. So the ultimate fate of a star like our sun is a white dwarf. Now, why I'm saying this? Because I'm going to mention a lot of these words throughout my talk, which are sun-like star, a red giant star, and white dwarf. And these could be the same star in just different stages of its evolution. Most of the stars that we see in the night sky are binary star systems. So there are two stars orbiting their center of mass, unlike our sun, which is a single star, and single stars are a minority in the universe. So here's an example of two stars, one that is ahead in its evolutionary track. So we have a sun-like star with a binary companion that is a white dwarf, and they are both orbiting their center of mass. Now, sometimes the sun-like star could also be more evolved, closer to the white dwarf phase, so it is a red giant. So we could have this red giant star with a white dwarf binary system. And these are common type of system. Binary stars with stars of different evolutionary stages are common in our galaxy. Now, sometimes, in some extreme cases, these two stars could be very close to each other, where the more heavy white dwarf stars, the dead star, will start absorbing mass from its living sun-like companion star. So we have a star cannibalizing its living companion, and we have a stream of gas that start going from one star to another, forming first a disk around the star before the material is dumped on the white dwarf surface. These are the type of stars where novae eruption take place. We have a white dwarf that is cannibalizing a nearby companion star, which could be a sun-like star, or it could be also a red giant star. But these are very close. In this case, if we have a sun-like companion star, the two stars will orbit their center of mass in a few hours, 3 hours or 2 hours. So they are really close to each other. This is a schematic impression of what we think these systems will look like. We have a white dwarf absorbing material from a nearby companion star via this disk that we call an accretion disk. The material is dumped on the surface of the white dwarf, forming a layer where the pressure and density increases with time as we dump more and more material, until a certain critical point where a thermonuclear eruption is triggered on the surface of this white dwarf, ejecting a lot of this material that has been absorbed on the surface of the white dwarf. And this is a nova eruption. Now, after the material is ejected, we have remaining hydrogen-rich material on the surface of the white dwarf, continuously burning. So we have nuclear reactions on the surface of the white dwarf, which would emit a lot of light, mostly in the higher energy X-ray light. But this light is then absorbed by this ejected material around the white dwarf and re-emitted in the visible and ultraviolet light. So we see a star shining in the visible light, a nova is born. After the eruption happens, what happens is that the system survives. So unlike the more powerful supernovae, for example, where we have an eruption that could completely destroy a star, here we have an eruption on the surface of the white dwarf. But after the eruption is over, the white dwarf will continue its old bad habit of cannibalizing its nearby companion, building material for the following eruption. So in a nutshell, novae absorb or accrete material, erupt, and then repeats the cycle. This cycle could take thousands of years typically to happen, but in some extreme cases, it could happen on a much shorter time scales, years or decades. And I'm going to touch base on this in a second. We discover many novae in our Milky Way every year. Between 10 to 15 novae are discovered in our Milky Way every year, and we might be missing even double that number. So novae are common, they are nearby, they are in our galaxy. Some of them, they are close enough that they become so bright that we can see them in the naked eye. Now, in the case when we have a nova that is having eruptions on short time scales, years or decades, we observe them multiple times in our observational records, and we call them recurrent novae. So when we say the word recurrent nova, it means the nova that we have observed going off more than once in our observational record. And this is very important, this type of novae, because this cycles of eruptions are more or less periodic to a certain extent, few years. So we can actually predict when they will happen next and give us a chance to be prepared to study them in more details. Now, when we look at a nova using telescopes that can observe in the visible light, we expect to see the light of a nova to show a quick rise to a peak and then decline slowly. This is an example I'm showing here, what we call a nova light curve. This is the change of the nova brightness versus time. And we see that the brightness of a nova increased with time and then started declining slowly. But not all novae behave like this. And we see diversity of behaviors from novae lasting at peaks for months or years. Some of them decline and then rebrighten again. Some of them show multiple flares or peaks in their light curves. And a lot of other features that we see in nova light curves, which keep us always puzzled. And Shaq's reaction here is actually each one of us reaction in the field when we see these light curves and we wonder what's happening. There's definitely something more happening than our basic understanding. So this basic understanding have been for decades that novae are these eruptions, the thermonuclear eruptions that occur on the surfaces of white dwarf stars that are absorbing material from a nearby companion. And most of the light from the nova is powered by this nuclear reaction on the surface of the white dwarf. But this has completely changed with NASA's Fermi Gamma Ray Telescope detecting high energy GeV gamma rays from several novae. And it was a shock for us, more like literally a shock, because in order to have this high energy gamma ray emission, we need shocks of that are formed due collision of gas clouds or ejected material from the nova eruption. So expect we have ejecta from the nova, ejected gas that are colliding into each other and causing these gamma ray emission. In more particular, these shocks would lead to particle acceleration within them. So we have ions or electrons that are accelerated. And when these particles, these charged particles are accelerated, they emit high energy photons in the gamma ray regime, which are detected by telescopes like Fermi-LAT. Now, why this is a shock? Because for so long, we did not think that novae could have such powerful shocks that could accelerate particles to these very high speeds, close to the speed of light, that would eventually end up emitting gamma rays. And the first nova that Fermi detected emitting gamma rays was a nova that have a red giant companion, not a sunlight companion, but a red giant companion. And these type of stars, if you remember, I told you they lose a lot of mass via stellar winds from their outer layers. So we thought that these shocks are the product of the nova ejecta colliding with this dense environment that has been enriched by the red giant star. So we have a lot of material pre-existing from the dying red giant star that has enriched the medium around the system. But later on, Fermi kept detecting more and more novae and detected novae that have what we call sun-like stars or main sequence stars. And these don't lose a lot of mass. So they don't have this rich environment of gas. They have actually little gas surrounding these systems. So astronomers in the field started wondering where these shocks are happening. And one of the current suggestions for these shocks predicts that these shocks happen maybe at the interface between two ejections within the nova itself. So we have an initial early dense slow ejection that is followed later by a fast wind which managed to move freely in the polar direction, forming this hourglass shape. And when these two ejecta collide, they create these shocks that eventually lead to gamma ray emissions. So we have now shocks that are happening between two ejecta of gas within the nova itself. Now, this is very important because we know that the shocks are going to heat up this gas. When these gas are going to collide, they're going to heat up and they're going to emit radiation possibly, mostly in the X-rays. But again, we think that these X-rays are absorbed by the gas around the nova and re-emitted in the optical. So now we have these shocks heating up the gas and radiating energy that will go out from the nova in the visible or what our eyes can see. Now, we don't know how powerful the optical emission should be from these shocks, or the visible emission. But based on how novae are bright in the gamma rays, we expect that the visible emission from these shocks should be really bright, that it could rival the emission from the nuclear reaction on the white dwarfs. So we have now an additional source of emission from the shocks that is contributing to the visible emission of the nova. And this is not new. Supernovae, stellar mergers, when two stars merge, tidal disruption event, when a black hole eats up a star surrounding it, all of these has been theorized to have shocks around them that emit light in the visible and contribute to their emission, but we do not have direct observational evidence until really recently in 2018, when a nova in our galaxy erupted. It's called V906 Carina. It was a very bright nova, almost a naked eye nova. This is the nova here. And we were very lucky with this nova because one of the satellites of the bright nanosatellite constellation, a constellation of CubeSats, this size basically, launched into space to monitor stars or bright stars for an extended period of time. And one of them was monitoring the star next to this nova. And what happened is that it caught this eruption, or this nova eruption that is happening, giving us this really nice detailed visible light curve of a nova, showing the eruption from its start and showing these multiple flares that are happening in the eruption. Now, to give you an idea how good this data set is, this is what the same nova look like from ground-based daily cadence observations. So these are taken from ground-based telescope every night. You see that they are not very well resolved, and we do not catch the eruption from the start. Now we have this really nice light curve in the visible. We were all waiting for Fermi to see if it detected the nova, but unfortunately, the night the nova erupted, Fermi was offline due to issues with its solar panels. But when it came back online after around 3 weeks, we got a really nice gamma ray light curve of a nova. So this is the gamma ray light of a nova, showing also similar flares to the one in the visible range. Now, the fact that we see these flares in the gamma rays and the visible, it means that they share the common origin. And the fact that we know that the gamma rays is coming from the shocks, it means that the flares here in the visible are also coming from the shock. Now we have evidence that the shocks contribute to the visible light from a nova, in addition to the nuclear burning on the white dwarf. That's great. How much is it contributing? Well, you see these flares look small, but this is what we call optical magnitude. And magnitude is a logarithmic scale. So actually, each small jump is actually a doubling in the brightness of the nova. So the nova brightness is doubling during these flares, which means that if these flares are coming from the shocks, it means that the shocks are indeed radiating a large fraction of the luminosity of a nova. Now, this set of data, which were unprecedented, provide us with the first direct observational evidence that astronomical shocks could actually contribute a lot of the visible light of a stellar eruption, whether novae or maybe other stellar eruptions. And also it tells us that all of these, or maybe some of these features that we see in nova light curves, like this example here, which puzzled us for a long time, now we know that they might have origin in shocks that are happening between ejected gas during the nova eruption. So Shaq, that was confused initially, now got some answers. Now, this new insight into novae, this new discoveries that Fermi has led, that Fermi Gamma Ray Telescope has led, means that novae are very valuable laboratories for us to understand a lot of mechanisms that are difficult to study in more distant events like supernovae and stellar mergers. So nova provide us with these laboratories in our galactic backyard to study a lot of physical phenomena. And also it means that novae could not only be multi-wavelength sources, but multi-messenger sources. When I say about multi-messenger sources, we talk about electromagnetic light, we talk about gravitational waves, and we talk about neutrino. And given that we have shocks in novae that are emitting gamma rays, and if these gamma rays are emitted by ions that are accelerated, novae could be sources of neutrino, which could be detected by current or maybe future neutrino experiments like the IceCube experiment in the South Pole, which is aimed at detecting high energy neutrino from astrophysical transient phenomena in the universe. Now, to end my talk and hand the torch to Chick, I mentioned earlier recurrent novae, and these are novae that happen more than once in our observational record. And one of them is the nova that you all are here today to learn about. It's called T Coronae. This nova, or T Coronae Borealis, this nova erupt on around 80 years time scale. So we can predict that it might happen in this year, plus or minus 1 or 2 years. And it's going to be very bright because it is quite close to us. The nova is at the distance of around 3,000 light years. I know this sounds a lot, but this is very close. And because of that, it's going to be very bright that we can see it in the naked eye. It's going to be as bright as Polaris. Now, this gives us a chance to study it in all sorts of facilities in space and on the ground, but also give you the chance to see it, not only enjoy it, but also you could use telescope to get data on it that you could provide to professional astronomers. I'm not going to go into the details, but feel free to ask me. I'm observing this nova from my backyard every night with small telescope, and this is something you can do with your students or you can do at home alone. So if you have any questions about how you could observe T Coronae Borealis from your backyard, please feel free to ask me after the talk. Thank you.
Okay, great. Thank you so much, Elias. Okay, take it away, Chick.
Well, thank you everybody for joining, and Elias for giving that introduction. I'm going to be talking a little bit specifically about the enchantment of T Coronae Borealis that has not only the professional community quite excited about the impending outburst, but also those of the folks in the amateur community and elsewhere that will be able to see this very interesting event. A little bit of motivation about why astronomers in general like to study explosive transient events in the night sky, and in particular recurrent nova. These are systems that in our historical record have been noted to go into outburst with some periodicity that's on the human time scale, so potentially individuals can observe an event more than once, is that they're really the third largest explosion that can occur in a galaxy. And in some sense, they're the largest hydrogen bomb in the universe because the source of ignition, as Elias mentioned, is the accumulation of hydrogen-rich material on the surface of the white dwarf that then detonates in a runaway thermonuclear type of event. And when this event occurs, this TNR, as we call it, occurs, the object markedly brightens and a new star appears and stays bright for periods of days to weeks to years before fading back to quiescence, hence the term nova or new star. And again, the recurrent novae repeat on an outburst cycle of perhaps several decades. Our T Coronae Borealis, which is the subject of intense interest in the upcoming 10 to 24 months, is one that has a periodicity of about 80 years or so. And these are the recurrent novae. As Elias pointed out, in these types of systems, we usually have a cool red giant star indicated on the right that forms an accretion disk around the white dwarf indicated by the bright object on the left. And then when we pile up enough hydrogen-rich material on the surface of the white dwarf, an explosion will occur, and in this explosion, we eject material from the surface of the white dwarf. That is a combination of the accreted material plus material dredged up from the surface of the white dwarf, and this ejecta can move out into interstellar space at very, very high velocities taking with it some of the products that are created as the thermonuclear runaway progresses on the surface of the star. Now, white dwarfs are the center of action in this event, and essentially the thermonuclear runaway occurs when gas from the cooler, larger companion flows onto the surface of the white dwarf. White dwarfs are actually very interesting astronomical objects. The theory behind what a white dwarf star actually is was worked out by Chandrasekhar on his boat trip from India to the United Kingdom to start his graduate residency at Cambridge. And they have a unique property that the size of the white dwarf decreases as its mass is increasing, which is an interesting little phenomenon. So as the object potentially accretes matter, its mass is actually changing. When we get enough material piled up on the surface of the white dwarf, the runaway thermonuclear reactions can occur in the secreted material and a giant explosion results. So again, the system will brighten dramatically, and to us, the observer, a new star will appear in a stellar field. And as Elias mentioned, our sun, when it evolves into that stage of its evolution, will evolve to a white dwarf mass of about half a solar mass when it becomes a white dwarf at the end of its evolutionary sequence. So white dwarfs themselves are something we can learn about through the study of nova systems in general. Now, one of the things that astronomers are quite curious of is the origin of the elements in the universe. The universe, in our current understanding, started off with a large Big Bang-like explosion, and through the evolution of stars as they go through their life cycle, we build up the elements that we now know on the periodic table that is indicated on the left-hand side from various sorts of stellar phenomena. Now, the origin of the elements can be looked at and examined from predictions of thermonuclear runaway theory. The basis of how stars generate their energy was worked out in the 1930s and 1940s. And we have quite sophisticated models now that lead us to believe and compute the various sorts of elements that appear on the table from various sorts of stellar evolutionary things, including the exploding white dwarf stars. We know that in novae, the ejecta is enriched in light elements in the ejected gas. We can predict the rough behavior of the light curves, as Elias indicated, where they rise from quiescence to maximum brightness as the eruption occurs and then decays over time. If we look at some of the elements that are produced in these thermonuclear runaways, the ejected material is enriched with very interesting elements like lithium and carbon and nitrogen and oxygen. And some of those latter sorts of species are actually pretty important in astrobiological settings. Now, when the eruption occurs, there's an X-ray outburst when the explosion occurs, and this is some of the events that were mentioned in Elias's previous conversation. And one of the puzzling questions that was already asked in the chat is, through this process, especially in recurrent nova who have very rapid, if you will, repeat timescales of accrete, explode, and recycle, can the white dwarf grow in mass to exceed the Chandrasekhar limit? The Chandrasekhar limit is roughly about 1.35 solar masses, where the star itself, if it exceeds that limit, is gravitationally unstable and will collapse. And so perhaps in some of these systems, the white dwarf could be growing in mass to become a supernova 1A type explosion, and that is predicted in some theories. And the reason that's astronomically very interesting is because supernova type 1As are standard candles in cosmology. They help us understand the size scale of the universe by measuring their relative brightness, assuming we understand the underlying explosive release of energy that occurs in these particular systems. And so do recurrent novae accrete more matter than they eject in an outburst because they have very rapid duty cycles is a very interesting theoretical and observational question that we can probe by observing these objects. As Elias pointed out, we have a rare opportunity to see T Coronae Borealis potentially in outbursts over the next 10 to 12 months. This is an image of where T Coronae Borealis lies. It's below Arcturus in the night sky, and that red circle indicates the region where the event is going to occur. It's about 3,000 light years distance, and the last reported explosion was in 1946. And it was detected jointly by, quote, a teenage boy out wandering in February looking at the night sky and a professional observer named Knight. And so really the focus of folks looking at the night sky, recognizing constellations and the transient objects that appear is quite important to the advancement and the understanding of the night sky, in particular transient events such as novae. Now, one of the things that we are going to be trying to understand is conduct a series of temporal observations after the explosion occurs. On the left-hand side is another very interesting novae that went off at the turn of the last century, which is GK Persei, and you can see the image of the ejecta, the central bright object that is ionizing the ejecta. So it's a false composite image, both in the X-ray, the optical, and the radio, that gives you a sense of what happens after these events occur. And GK Per was interesting because it was one of the brightest stars in the night sky in 1901 when it erupted. Now, T Coronae Borealis, based on historical record, potentially could reach a visual magnitude of about 2, which means it will brighten from its quiescent state, in other words, its existence in the background, by over a factor of 1,000,000 when it erupts. And so this should be a very interesting event. Now, in particular, a number of NASA assets will be used to study this event. We will be using the NASA Swift-Garrels X-ray Observatory, which is an X-ray and UV photometry and spectroscopy platform. And one of the nice things about using this particular facility is that we can look at the emergent energy in the X-ray and estimate the temperature of the emitting ionizing source by studying and fitting the X-ray emission. So what you see in the top slide here is a spectral energy distribution. It counts on the vertical axis and energy on the horizontal axis, and each one of those crosses is a measurement, and then we try to fit that with a model that tries to estimate what the underlying temperature of the object is responsible for that emission. In this particular case, one would get a black body fit of about 276,000 degrees Kelvin for this particular source V1716 SCO that was observed with this X-ray telescope. The bottom image is a ratio of the model versus the fit. And so that shows you how well we can sort of estimate the temperature of the hard ionizing source after the eruption occurs by using a platform like SWIFT. Now, in particular, we were fortunate enough in cycle 3 to have a proposal awarded for time on the James Webb Space Telescope. The James Webb Space Telescope is one of NASA's newest assets in its portfolio, and it's an infrared imaging and spectroscopic platform. Part of the reason that we would like to study this particular object with the James Webb Space Telescope is this object has never been studied in outburst in the infrared before. In 1946, when the last eruption was noted, and astronomers slew their telescopes to it, we were still using very small aperture ground-based telescopes. And in the aperture, where one would stick one's eye, people were putting glass plates that had photographic emulsion on them to try to record the spectra that they saw. What you see on the left-hand side is a panel in the infrared where James Webb operates, spanning the wavelength regions from 1 out to about 20 microns, and intensity is on the vertical axis. And the red arrows indicate the wavelength range of 2 of the spectrometers that are on the James Webb Space Telescope that potentially could be used to study this outburst. The curve in blue and yellow is an example of what we would call a spectral energy distribution of a nova as the ejecta is expanding and having material condense out of that hot gas into solid state dust features. And one of the things that we're very curious using particularly the MRS spectrograph is to try to understand in the ejecta of T Coronae Borealis, do we actually condense particulate matter? And that's one of the things that we're going to be looking at. The other thing is, because recurrent novae undergo periodic ejection of material, there might be an opportunity to observe a light echo, very similar to what was seen in V838 Monocerotis on the right-hand side that was recorded with the Hubble Space Telescope, where light from the detonation on the surface of the white dwarf is reflected off prior shells of emission and reflected into our line of sight. But because T Coronae Borealis has never been studied at these wavelengths in outburst, what we're really going to see is somewhat of a mystery. And this is part of the excitement of studying transient events. Although we have some general idea of how these systems explode and then evolve, each individual system provides new insight and understanding to how these events actually occur. And in particular, with the James Webb Space Telescope, we're interested in addressing 4 fundamental questions. What we're really trying to use this platform for is to further our understanding of these recurrent novae in general. In particular, recurrent novae, if they can accrete enough mass, could become a supernova type 1a. So we're trying to explore potential links between recurrent novae and these very important cosmological standard candles. By studying these systems over time as they evolve, it provides us insight into the evolution of the systems and potentially perhaps points us a way to understand type 1 supernova 1as that are key to determining cosmic large-scale structure. So with the James Webb Space Telescope, we'll observe properties of shocks propagating through the ejecta. We can measure changes in the velocity profile, the emission lines. We can look at these features called coronal emission lines that are very similar to the coronal emission we see in the sun from highly ionized elements. That allows us to derive the elemental abundance that this TNR produces in this explosive runaway. And we can also look at what type of dust might condense in the expanding ejecta. So we're hoping that the James Webb Space Telescope will provide some unprecedented insight into the details of this nova's expanding fireball. And as Elias pointed out, not only are professional astronomers quite excited about this event, but it provides an opportunity for citizen science activities. On the left-hand side there, you see a discovery image of a nova in Delphinus in 2013. The upper panel is a picture before the explosion, about 1 day, taken with a very small telescope, 60 centimeters. And then you can see how bright the object has become. And this was part of a study that an amateur was doing and then reported it through various email channels and other channels to the professional astronomers that began to observe it. Now, NASA itself has a night sky network. You can see that there's a link there and you can explore that. For those that aren't quite familiar with the night sky, there's many apps that you can get for your digital devices that will help you identify the constellations and locate where T Coronae Borealis is going off. And one of the opportunities this provides is for many people with small telescopes, cell phones, and even the naked eye to watch how this object will evolve over time. And there's various portals that one can submit their observations to, such as the AAVSO, the American Variable Star Society. The ARIES network is a network of amateur astronomers using telescopes like those on the right that have spectrographs that will record the spectral evolution of the event. And those data are quite interesting to everybody who likes to study these transient phenomena. So with that, I will conclude my conversation, and we can have the last slide, and I'll open it up for questions and comments. Thank you.
So yeah, thank you so much, Chick. So if anyone has any questions for our speakers, you can put them in the chat right now and I will read them out. So I think there was one question in the chat that we didn't answer with the slides, and that, I guess, is one of the most important questions. How is a nova different from a supernova? So maybe Elias, you want to take that?
Yes, actually, I had backup slides for this particular question because I knew someone was gonna eventually ask the question. So if these are two videos of, I showed one earlier of a nova, which is, as we've been talking, is a thermonuclear eruption on the surface of a white dwarf. However, a supernovae, we have different type of supernovae, but the two main type are something that showing on the right hand side video, which is what we call a core collapse supernovae. And this has happened when we have a massive star. So we have a star that is 8 times or more the mass of the sun. When it reaches the end of its lifetime, the star is going to turn into a giant star, or a red supergiant in this case. And then once the star cannot burn more elements in its core, it's going to lead to a collapse of the outer layers of the star under their own gravity, bumping on the core and then sending a shock through the star. This is what we call a core collapse supernova. And these are going to lead to ejecting a lot of material, much more than novae eject, which is going to enrich the interstellar medium. And also they're going to be much more energetic, as Chick pointed in the chat. And also from this, we're going to have the remnant core is going to turn into a neutron star or a black hole. Now, the other type of supernovae, which relate more to novae, and Trick was talking about them, and this is I have in the next slide, which is what we call type 1a supernovae. These type of eruptions happen in similar systems that host nova eruptions. So we have a white dwarf star that is absorbing material from its companion star that is most likely a red giant. And as this system experience maybe more nova eruption, if it's gaining mass with time, it's going to reach to what Chip told us about, the Chandrasekhar mass limit, and this is around 1.3 or 1.4 times the mass of the sun. And if the white dwarf gain enough mass to reach this mass, the white dwarf is going to completely detonate in one final explosion. That is the type 1a supernova. So the system here is not going to survive, and the white dwarf is going to detonate, unlike a novae where the systems survive. Now, there's another channel of having type 1a supernovae. Instead of a white dwarf cannibalizing a living companion, it might be two white dwarfs merging, forming a larger or heavier white dwarf, more than 1.4 times the mass of the sun. And the merger of these two white dwarfs is going to detonate into a type 1a supernova. This is briefly the main difference between novae and supernovae. But I always like to say the main difference is that in novae, the system survives. So we tend to see more novae happening. However, in supernovae, it's a one event that the system does not survive.
Okay, great. And then I guess there's another question in the chat. Then what about a kilonova? So we've talked about novae and supernovas. So then what's a kilonova?
Yeah, that's the problem with astronomers naming things between novae or classical novae, supernovae, kilonovae, dwarf novae. It's more or less about the energy output, but also kilonova is typically the outcome of a merger of two neutron stars. So this was an event that was observed for the first time in 2017 in both electromagnetic light and also in gravitational waves by the LIGO experiment. And this was the first, like, or if you want, the beginning of multi-messenger astronomy, in a sense that astronomers became really interested in studying events that emit not only electromagnetic light, but also other messengers like gravitational waves or neutrino. So a kilonova is basically the merger of two neutron stars.
Okay, great. And we have maybe one final question before we go into the resources. And that maybe, Chick, you can take this one. How many recurrent novae are there in our galaxy, and how often do they erupt? Is it decades or centuries?
Well, I put a slight response in the chat, but there's about a handful of recurrent novae in our galaxy. Others that we regularly study are objects like RS Ophiuchi that has a duty cycle about once every 25 years. V3890 Sag, sorry, I have to keep all these telephone numbers in my head, is another example of a recurrent nova system. So there's a handful in our galaxies. And get back to one of the questions that was asked in the chat. The amount of material that the white dwarf will accrete between eruptions is of the order of about 10 to the minus 7 or so, or 6 solar masses per year. So if you multiply that by 100 years, you can figure out potentially the total mass that the system might accrete. And from our understanding and analysis of observations in the explosive ejecta of material, that's only of the order of maybe 10 to the minus 5th or 10 to the minus 6 solar masses of material in a single ejection. So over a longer lifetime, galactic lifetime, actually you begin to get an imbalance in the material accreted onto the surface of recurrent novae and the amount of material that's actually ejected. So you can actually tip the scales and fall over the boundary to have the object completely collapse. And this is one of the contentions that theory and observation are wrestling with, because the theorists say, well, our code is right because we understand how these things produce elements, and the observationalists say, well, this is what we observe. And so there's a tension here that we're still trying to ascertain. And because potentially these are precursors or progenitors of supernova type 1A systems, we would really like to understand fundamentally their origins through whatever pathway they arise from.
Yeah, and as I said in the chat, that is the question that really got me obsessed with novae. So I was, during my PhD, studying type 1A supernova progenitors, and I wasn't focusing on novae, but then like I was like, oh, but wait, do they actually end up exploding the white dwarf or not eventually if you give them enough time?
Right. I think like anything, there's a continuum.
Yeah.
There's continuum, our nomenclature, as Elias indicated, that we're very creative. But these objects that are new stars are all sort of given the title novae, and how each event actually occurs, they sort of aggregate into different taxonomies that astronomers like to study, because by studying large populations of systems, you can get to some of the underlying physics that drives them and help us understand our universe writ large.
Very cool.
I want to add something very quick, a fun fact for the audience. So we talk about the recurrent novae in our galaxy, and maybe like the fastest ones are recurring on the order of a couple decades, maybe. But in our nearest galaxy, Andromeda or M31, it also has several novae that happens every year. And also it has recurrent novae, and it has one extreme case of a recurrent nova that erupt every year. So it is the most extreme case we know of in the universe, and it is a nova that recur on a yearly time scale. And this would make it maybe the best candidate we know of for a nova to turn into a type 1a supernova, maybe in 100 million years from now. So this is not in our lifetime, but this is one of the most extreme cases we know of in the universe for a nova to erupt every year.
Cool. Okay. So I would like to talk briefly about the resources that we have from NASA and NASA's Universe of Learning. I put a link in the chat that has NASA's Universe of Learning page that has the slides that we just presented today, along with a resource document. And those are also posted on our partner websites as well. So the first thing that I'd like to highlight is there's a couple of news articles that talk about T Coronae and our excitement building up to this. And then there's also links here. So NASA's Goddard Visualization Studio actually has some really great movies and images of novae that you can use. They're all in the public domain, so you can use them however you want. And we saw some of them in the presentation today. So there's links to those videos and stills. And this is something that I would really like to highlight myself. So there is a Girls Steam Ahead with NASA program cookbook. So if you are doing any programming around this, say the nova actually goes off in the next couple of months and you want to set up your telescopes and have a star party and you want to do something else and talk about maybe the life cycle of stars, there is a whole host of activities. So this is what you can find in the Girls Steam Ahead with NASA cookbook. So there are links to all sorts of different activities that you can pick from and ideas about how you can run your own programming. So this is branded for girls and their families, but a lot of these activities will work with all sorts of different audiences. Two favorite things that I have done with different audiences is a stellar life cycle bookmark. So there's a bookmark printable that you can have, and then you can take beads and string them along to talk about the life cycle of stars. And then at the end, all of your participants have a bookmark that they can take home with them. And maybe if you want to add something in there for exploding stars, you can do, I don't know, a glittery bead or something. And there's also a stellar evolution flipbook that you can make. So there's a version that's already colored in, but there's also a version you can color in yourself. And so you can cut that out and do that with the people in your at your star party, and I think that's also a fun thing to do. And so here are some more NASA resources on the life cycle of stars. So understanding the evolution of low mass stars, how we get a white dwarf and how we get novae. And there's also AstroPix, which is an excellent resource, which I think is a hidden gem. So you can go in there, you can type in nova, and so that's the link that we have here is images of novae that have been previously published all across different NASA websites. But also you can type in your favorite astronomical object and you can get professional astronomical observatory images for just about anything that you can think of in space. And so it's a really cool resource. It'll tell you what wavelength it was taken at. It'll give you more details and it'll give you a link to the original site. So it's a really cool resource. I suggest that you check that out as well. And so this here is a link, which I already put in the chat, to our Universe of Learning resources page. And there's even more resources than I had to talk about today. So go and check those out to use for your own audiences. So your feedback, we would like your feedback about how things went today, what you liked, what you didn't like. This helps us plan future briefings to appease the data god. So please go to this link. We'll also send you a link after the briefing, and we would like you to take 5 minutes to fill out this survey to help us out. And I guess with that, we can end on our last slide. So thank you, everyone who came. Thank you again to Elias and Chick for giving us really great presentations. And yeah, I hope this thing explodes soon. I'm excited to see it, but I really don't want to jinx it. Because the easiest way to get a nova to not explode is, of course, to predict that it will explode.
Okay, well, thank you.
Thank you, Kelly, for organizing this.
Yes, thank you.
Okay, bye everyone.
Thank
Bye-bye.
you. Bye.